Okay, now we're ready to talk about that second part of 11.5, which is a little different, and it relates a lot or very similarly back to some proofs you were doing in geometry, but this is called mathematical induction. All right, so taking a look at our process here, you can see that this is going to be proving, and we're going to prove that a statement is true for all natural numbers n. You really need to follow two basic steps. And probably shouldn't say basic because that's part of the definition, but here we go. In the first step, which is called truly the basic step, you want to show that the statement you're given is true for n equal to 1. So you have to come out and show the statement does work for when your n value or natural number is a 1. Then the induction step, step 2, you have to assume the statement is true for a natural number k. Okay, so we do that. We basically change and put a substitution step in and show that. And we don't know what k is. K could be the first 5 natural numbers. K could be the first 1,000 natural numbers. Then you have to prove that it's true for the natural number k plus 1, which is the immediate next value. So if you assume that it's true for the first k, then it's your job to prove that it's true for the k plus 1 term. All right, knowing that, we're going to try a couple, and then we're obviously in class going to share some too. So here we go. If we said, prove the following statement. For every natural number n, 5 plus 11 plus 17 plus etc., etc., and we're saying we're generating these terms by nothing more than 6 times your natural number, subtract 1. So if you would have put a 1 in to that, 1 times 6 was 6. 6 minus 1 is 5. So that's how we got the first term. Then if we put a 2, which is the next natural number in, 2 times 6 is 12, subtract 1 is 11, and we get our second term. Third term, 6 times 3 is 18, minus 1 is 17. And we keep that process going right on through. So it says if you really add all these numbers together that are generated from this expression, you should get as a result n times the quantity 3n plus 2. So this first one I would highly recommend you write down in detail, and then when we have to do one together, we'll be able to follow this example, use it as our guide on some of the others. Okay, here we go. We need to do that first basic step, which is show that this is true for n equals 1. So we take the left-hand side's first and only term that we're going to be doing, so 6 minus n, or 6n minus 1, and then it has to be added up to n times 3n plus 2. And it said for n equals 1, for one term only. So 6 times 1 is 6, take away 1 is 5. Do that same thing here. We get a 1 in for n in every slot, and we do the math. 3 times 1 is 3, plus 2 is 5. 5 times 1 is 5. And so we get 5 equals 5, which is definitely a true statement. And so now we have to go with the induction process. So now we have to assume it's true for all natural numbers k. So if you notice, from that original line up top down to this line, the only difference is that instead of an n, you now have a k. So we still have 5 plus 11 plus 17 plus dot, 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 standing for all those other terms. But when we get out there and we're generating, we're doing 6k minus 1 rather than the n. And on the end sum statement, we're saying k times the quantity 3k plus 2. And I've underlined that k times the quantity 3k plus 2 because that will come into play as we work forward. So we're assuming it's true for that. Now, prove that it's true for k plus 1. So for the next term in your sequence. So start thinking, what would our sequence look like if we put a next term in? And if you can see here that that sequence would be nothing more than this 6 times k plus 1 minus 1. And you're going to say, well, I don't see where you get that exactly. Well, watch over here. Try to use a number that we can see. If our last term was 6, if our last term in our sequence of the original sequence was 6k minus 1, then we would have to put that k plus 1 in for just k, and then subtract. So we're doing a substitution, and if we multiply, 6 times k is 6k, 6 times 1 is 6, subtract 1. So some people might even call that 6k plus 5, but we're going to leave it as listed right now. But if you added that term to the left side, you must also add it to the right. So you're still seeing the same sum that we saw originally, but since we added a new term here, then we must add that same term here as well. So if we add something to the left-hand side, we must add that same thing to the right. That's our normal algebra. So let's look at what we have. So now I'm only working off the right-hand side, and we're trying to get it to match, so to speak. So if I have the 3k plus 2 times the k, I'm going to go ahead and multiply that out, and you can see 3k times k, 3k squared. K times 2k, keep multiplying. 6 times k, 6k, 6 times 1 is 6, and then we have that subtract 1. Keep simplifying. We get 3k squared plus 8k plus 5. We can try to factor that. It's nothing more than a quadratic. And we factor it into one combination only, and that was k plus 1, 3k plus 5. If you look, though, that k plus 1 is really nothing more than that 3 times k plus 1 plus 2. So if you rewrite this piece, it would simplify to 3k, because that gives you 3k. 3 times 1 is 3. So we're taking the common factor out and just leaving that 2 there. This breaking up step is the hardest one for you to do, going from here to here. You got this answer, but now you have to think and say, well, how is that related back to that k plus 2 look that we were going for on our sum? So k plus 1 and 3 times k plus 1 plus 2 is truly of that same form that we had above. So this is the k, but now it's k plus 1. This is the 3k plus 2 term, but now it's k plus 1. So it's showing us, yes, really, that k times a quantity, 3k plus 2, or 3k plus 2 times k, it's really in that form, which is why it works, and we have just proved it. Now, that's a little tough, but that's where we are headed. Okay, so we are going to be working in groups here in class, and we want to prove this. So if you want to take a look at it and try it, how you would write it, but we are going to break a couple of them down in class together and see if we can prove them. We're going to work together because, as we say, more heads are better than one. You want to get used to it. It's a process similar to proofs, so that's what's going to make it a little tougher. So that's the basic form of how they have to be written, and that's what we'll be looking for in our work. So bring those questions to class and be ready to practice induction proofs.